Welcome everyone for Cloud Computing and Big Data. Today we have our lecture 13, and it's my pleasure to introduce you to Marcel here on the call today, who is providing you the lecture. And he's really an expert in hyperparameter optimization and AutoML techniques. He did this through his PhD. He's almost completed and is definitely an expert to talk to. So Marcel, welcome here. Can you maybe talk a little bit about yourself? And then we come back to the lecture.
Yes, thank you, Morris. Hello. Yes, I'm Marcel. I'm a PhD student from Morris here in Iceland at the University of Iceland. And at the same time, I work in Jülich at the Jülich Supercomputing Center in the Simulation and Data Lab of Fluids and Solids Engineering. And the main topic that I covered during my PhD was how to perform efficient hyperparameter optimization for scientific machine learning workloads on HPC systems. So that's also the topic that I'm going to cover today in this lecture.
Exactly. And thank you very much, Marcel, for doing this. I think you could be also one candidate for those of you here in the students class that might be interested in a PhD. So maybe I can also refer to you, Marcel, then they should maybe talk to you that they understand a little bit what the life entails as a PhD student here. But before we go, let's say in the material of today, let us maybe connect what we had the last time in lecture 12. And if you remember, this was really reviewing a little bit the concept we introduced a bit earlier in the course. It was about containers. And then we put them aside a little bit, the virtual machine concept, right? The virtual machine concept, virtualization fuels cloud computing a lot. That's what we said already in the beginning of the course. If you remember, with many benefits. That is, of course, with the idea of the applications that you can put there in a sort of sandbox, everything prepared. You have seen the AMI, let's say, images we have used even in the different, let's say, hypervisors from AWS, for example, but also, of course, MS Azure and also Google Cloud has different already provided images. Now, what we did then the last lecture was to go one step further of the idea of using containers. And they're similar. And of course, in one respect only, in another respect, you have learned, and this is also shown here in the graphic, that when you compare really virtualization with containers, one of the major elements is really that you don't have to carry around the guest operating systems anymore. That was one of the major findings. You see that here on this basically illustration, that we still focus on the, let's say, applications, the different binaries and libraries we need for them. But we instead having now not a hypervisor where then the virtual machine comes alive as guest operating systems. Instead, we have a so-called Docker engine. And this engine then sits like the hypervisor we learned also on a host operating system. So this is, of course, still needed, as well as the real hardware infrastructure. You know that in cloud computing, we need still real hardware somewhere. But here, the idea is that the Docker engine significantly helps to let's say, shrink the size on disk of these images, for instance, because you don't carry around the guest operating system anymore, and you have a very low overhead, and you basically pull dependencies from software as needed, and basically can have a very nice modular approach to applications, as the, let's say, container ship there that you see, and we often see in Iceland here from Imeskip and so on, suggests. So it's also an approach to really enable migration, portability from one cloud to another, perhaps much better even than virtual images are doing, because you know the AMI image we had in AWS, this would be not directly transferable essentially to Google Cloud, right, or also to the MS Azure ways. But the Docker container, chances are that if you configured it well, that you can actually use it also in all the different hypervisors and beyond, because we also talked about in the last lecture, you see that here below is UberCloud, for instance, that there are, of course, now also different vendors using these Docker technologies. We talked a little about the different nuances, also about Aptainer, for instance, and Singularity, which we, for instance, have also in the Jülich Supercomputing Center, so you can even bridge from cloud to essentially HPC environments. Then a little bit the discussion was, of course, looking more on how this is all managed. There's a, let's say, other type of software which has so-called kubelets. It's a Kubernetes idea of running then, let's say, different Docker nodes together on Kubernetes with a, let's say, more management approach of bringing these different Docker containers together in a larger scale, managing them at scale and have a better control, where lots of automation takes place as well, right? So, and this is something what we reviewed also in the Google Cloud, when we looked a little bit, what is their support in terms of containers, right? You have seen there's a Kubernetes engine that then takes care of the whole development process, that has an automated deployment. You have container registry services. So you see that hypervisors really have adopted these inherent concepts from using firstly the containerized approach with Docker, and then also often the Kubernetes way of managing it. We have seen also sometimes Mesos is also put on it. But I think that's all in a way I also wanted to leave on the table for you for lecture 12, because then what we want to do today is to connect nicely to other areas where we had stopped. You remember in deep learning, lecture 6, lecture 7, lecture 7.1, exactly, thank you, Marcel. We have stopped in a way and said, well, you could further tune deep learning applications, get maybe better performance when you do hyperparameter optimization, right? And this is exactly the topic I was referring to that we have today, where we use tools like also Marcel will allude to with RayTune and so on to really make even not just the speed up with clouds possible, so make it faster, but make also the AI modeling, the deep learning models much better in terms of performance, accuracy, and I think that Marcel will talk to. So I give it over to you, Marcel. Thank you very much again for doing this, and go ahead.
Thank you, Morris. Yes, so the lecture today will have two parts again. In the first part, I will give a general introduction to hyperparameter optimization and automated machine learning, covering things such as what are hyperparameters, which algorithms there are, which kind of adaptive scheduling algorithms there are, and which kind of adaptive selection algorithms there are, and also give you a bit of guidance of when to use which algorithm. And in the second part, I will show you some examples of how we applied hyperparameter optimization to actually scientific applications and improved the performance of machine learning models there. Introduce you to the RayTune library that can be used for distributed hyperparameter optimization. This tool is especially important for cloud and HPC environments because of this distributed aspects. And then briefly, we will also touch upon the AutoGluon tool, which is a library from Amazon and is designed specifically for tabular data. Okay, so to make sure everybody's on the same page, let's start with the question, what are hyperparameters? So in machine learning, the hyperparameters are the parameters that are usually set by the user before training a machine learning model. And these kind of parameters heavily influence the learning behavior of your model. And those things can include, on the one hand, architectural parameters. So which type of machine learning models you use, if you're using neural networks or support vector methods, for example, the number and the kind of layers, whether you're using convolutional or regular fully connected layers, for example, and things such as neurons per layer or also the activation functions, of course, are also hyperparameters. And more prominently, hyperparameter optimization refers to the parameters of the optimization process. So this includes the type of optimizer. So for example, whether you're using stochastic gradient descent or ADAM. But yeah, probably the most important hyperparameter of the optimization process is the learning rate. But there are other things, also momentum or weight decay, for example. But actually, that's not all. So if you really want to do automated machine learning, then you maybe also want to include the parameters of the whole machine learning pipeline into your AutoML workflow. So that would not only include the parameters I just mentioned, but also parameters of the, for example, data preprocessing, such as image size, image normalization, cropping of your images, or the image rotation. So each of those functions you can include as an optional parameter and then check or optimize your model for the usage of those preprocessing parameters. So to put it all into perspective, there are in total 3 areas where you can tune predefined parameters. The first thing is the so-called neural architecture search. So if you're doing neural architecture search, you're just looking at the architectural parameters, such as the neurons or the number of layers. Then we have the so-called classical hyperparameter optimization, which includes architectural parameters, but on top of that also optimizes for learning rate and so on. And then if you, as I just mentioned, also add parameters of the pipeline on top, you get what is commonly referred to as automated machine learning. If you've ever trained, especially a neural network, then you probably know how important hyperparameters are for the success of your training. And to visualize it again, here's an overview of the learning behavior of a very simple neural network, a ResNet, which is trained on the Cypher10 dataset. And you can see here that you see here how important the learning rate is just for the behavior of your neural network. So basically, just picking the right learning rate here makes a difference between getting a model that achieves above 80% classification accuracy, which is very good, and a model that just achieves maybe 10% classification accuracy, which Cypher10 has only 10 classes. So in this case, the model produces just noise and does not learn anything. So what you want is to pick a good learning rate. Otherwise, you maybe have a good model, but because you chose the wrong learning rate, it doesn't learn anything. And this plot actually already gives you a first hint why the problem of selecting the best hyperparameters is so hard. And that is that there's usually not a general prediction possible. So you see the 2 top learning curves here, the orange one and the blue one. They have learning rates which are very different in terms of size. So one is rather small and the other one is rather large, but both get high accuracy. And on the other hand, when you look at, for example, the green learning curve here, which is very similar in terms of size to the blue one, but we see it gets a lower accuracy of, clearly below 80%. So often in hyperparameter optimization, it's not possible to say large learning rate is bad and small learning rate is good, but you really need to find the optimal values for this. A bit of terminology. So when we do hyperparameter optimization, we first would define a search space, which defines the hyperparameters and the range that we sample these parameters from. When we talk about a configuration, that means that we sample, we take one sample from this search space, and then we do one training run on this configuration, which is then referred to as a trial. I want to mention already at this point that in this workflow, it's very important that you have separate data sets to do these different steps. So you want to have one training set that you use for the training of your model. Then you want to evaluate the performance of the different configurations of the different models with the different hyperparameters on a separate validation set. But then to get your final score that you report at the end as your model performance, you would need a third, completely untouched data set. So either another validation set or an untouched test data set. And this is important because once you make the selection of which hyperparameters you choose on the validation set, that choice is, of course, that the validation data set is, of course, already used. So you need to basically throw it away and evaluate your performance on your final performance on another data set. The main reason, or there are several reasons why hyperparameter optimization is hard. The first one is that the search space of the hyperparameters is usually a mix of lots of different types of parameters. So you have the architectural parameters, such the number of layers, which is, of course, a discrete value. You can choose any integer value for this. But then when you look at the learning rate, it's usually a continuous value. And yeah, you can choose any floating point number for this. This also means that usually you cannot compute gradients like we do when we're training the neural network, where we're using gradient descent to find a minimum. So instead, you need to find other optimization methods. The main reason why HPO is so computationally expensive is that you can only evaluate with certainty the performance of your model after you've performed a full model training run. And this, of course, can take some time because you need to essentially train your neural network, for example, for all the epochs to say if your hyperparameter combination is good or bad. And those two reasons, so this mix of search space and the costly evaluations of the trials, and probably because there's a general lack of guidance on how to approach a systematic HPO, to this day, many machine learning researchers still tune their hyperparameters via trial and error. So you as a developer, probably when you train the models, you choose some parameters, then you train your model, you look at the score, and then you tweak the parameters and train it again and so on. But yeah, this is, of course, not a systematic approach. So how can we do HPO in a systematic way? The easy or naive way to approach this problem is to do either random search or grid search. So in random search, as the name suggests, you just sample randomly configurations from your hyperparameter search space, while with grid search, you evaluate every possible combination. The interesting thing here is that especially random search is a very good starting point. So when you don't know anything about your problem or don't want to spend time implementing more sophisticated methods, it's always a good idea to at least do random search. Both methods are, of course, embarrassingly parallel. So there is almost no communication between the different trials necessary, which means, that they scale very well when you add more parallel processes to your run, which when we're working in cloud or HPC environment is, of course, something we want. But especially grid search, of course, you're wasting lots and lots of computing resources on very bad hyperparameter combinations that you probably shouldn't train. So how can we accelerate this? There are, to make in general HPO more efficient, there are two approaches. We can either do an adaptive selection of the configurations that we want to evaluate. So this means using Bayesian optimization or evolutionary optimization to step-by-step pick better hyperparameter configurations to evaluate. The main problem we have here is that our search space is very high dimensional. So if with each hyperparameter that you add to your search space, you're creating a new dimension. And this high dimensional problem can make it hard for some of these methods to converge. And the other option, which we will focus mostly on here today, is to perform an adaptive scheduling of your trials. This means that you stop trials with a bad performance early on and instead use their compute resources for trials with better performance. And the main problem that we run in here, of course, is how can I decide which trial is bad and which trial is good when I don't have much information about my problem available? And the first hint you can already get from looking at these learning curves. So you see that when we have lots of learning curves available, lots of data available, we can of course say that some trial is better than a lot of other trials, or some trial is worse than a lot of other trials. So we really need parallelism at this point to show for us to make a good decision on which learning curve is a good one and which one is a bad one. And this is where the first scheduling algorithm comes into play, which is called successive halving. The basic idea here is very simple and based on the concept of early stopping bad trials and allocating their resources to more promising ones. And it looks like this. So over the amount of epochs, you have several steps in time where you look at the current performance of all of your trials. So here we are looking at the loss, and of course, the lower the loss, the better. So maybe after 10 epochs or so, we look at the current loss values, and then we just terminate, let's say, 50% of our trials, and instead only keep running the best 50%. And then we train for another 10 epochs, and then do the same thing again. So look at the current performance of our trials and terminate the worst half of them. Yeah, and when we look at this picture, then when we repeat this process at multiple points in time, we hopefully end up with just one trial in the end with this dark green line here, which would then give us the model with the lowest loss, but we would get there much cheaper because we have performed early stopping on all the other not so promising trials here. The main question here is then, how do we balance our computational resources? Should we maybe in the beginning run more trials? Or should we do less aggressive successive halving and to get more exploitation and run all the trials for longer? So this is where Hyperband extends the classical successive halving approach by performing successive halving with different levels of aggression. So what this means in practice, that you maybe have a small number of hyperparameter configurations that you train completely without any early stopping. Then you have a larger amount of configurations that you train with one successive halving step, an even larger amount of configurations that you train with two successive halving steps. And then in the end, you train a really large amount of configurations, but with 3 successive halving steps, so with a large amount of aggression. And the idea of this hyperband algorithm is also that you hopefully can catch trials that start out weak but get strong later on, and do not accidentally terminate them early. So when we go back and look at these loss curves here, we see, for example, that in the beginning, there is a loss curve here that shows a very promising performance, but then afterwards, it actually gets worse. Maybe here this blue line here it shows a very steep decrease in the beginning, but unfortunately, we have the first successive halving point at this point in time here, and we terminate the trial. But it could, of course, be that it only starts catching up later on, and in the end, maybe give us the lowest loss. And of course, we want to avoid this. So that is why we are doing hyperband with these multiple levels of aggression, basically. But when you're moving to a setting where you have lots of parallel resources available, for example, on HPC systems or in the cloud, you will actually run into performance issues with this classical hyperband approach. So at each successive halving point where you're performing early stopping of your trials, with the classic hyperband, you need to wait for all of your trials to reach this time barrier, essentially, before you can make the decision on which trials to continue and which trials to terminate. When you have trials that are slower than others, for example, because they train a very large model, this, of course, can lead to bottlenecks, because all of your trials at this decision point in time need to wait for the slower ones. So the method is very sensitive to stragglers. And when you're working on a system that has many parallel computing resources available, you probably have lots of trials running in parallel. And then you waste lots and lots of resources at each of these time barriers, just waiting for the slower trials to catch up to the faster trials. We therefore need to move to an asynchronous setting. And what the asynchronous successive halving, the ASHA algorithm, does is that at each of these decision points in time here, it immediately looks at the performance of the incoming trials, and then based on the current information it has, decides on whether they are allowed to continue or whether to stop. And there is a nice visualization of this. I also want to give you a brief overview of adaptive selection methods of hyperparameters. And here the idea is to build a surrogate model that is cheap to compute, but which can mimic the performance of the original machine learning models. And for doing this, there are many different algorithms and libraries available, especially in the field of Bayesian approaches. So just to give you a few examples, there's SMAC, Dragonfly, or Optuna. But the main challenge they all have to deal with is how to handle lots of parallel results coming in, as Bayesian optimization is usually a sequential process. And as already mentioned, Bayesian optimization sometimes has problems in very dimensional search spaces. But for example, the deep hyper library here is also one library that seeks to tackle this issue on larger scales. Of course, you can also combine Bayesian optimization with the hyperband method I just introduced to increase efficiency, which would then yield something like the Bob method that basically uses hyperband for the scheduling of the trials, and then Bayesian optimization for picking which hyperparameter configurations to evaluate. A special case I would also like to address are non-stationary or dynamic hyperparameters. So the ones that change during the actual training of your model. The prime example here, of course, is changing the learning rates over the number of epochs. So you probably don't want to train with the same learning rate in every epoch, but you want to have a schedule. There are lots of predefined schedules already available, like cosine annealing or exponential or stepwise annealing. But maybe you want to design your own schedule. And in this case, something like evolutionary optimization is something that's interesting to look at. Here we're using population-based training, which was originally introduced by Google DeepMind. What we do here is that we start out with an initial population of trials, which is trained for a certain amount of time. Then again, we look at the relative performance of each trial. So how good is this configuration compared with other configurations? And we terminate the worst 50%. And what makes this approach special now is that the trials with the bad performance, after they have been terminated, they copy the state of the well-performing models. So including architecture weights and the current neural network weights, they copy everything and then apply small mutations to the hyperparameters, such as changing the learning rate by a very small factor. And then you again do that multiple points in time. And then in the end, you hopefully end up with a series of learning rates, which gives you your learning rate schedule. In general, this approach is referred to as evolutionary learning. And of course, there are also lots of other libraries that do similar things for hyperparameter optimization, such as Nevergrad or Propulate. Okay, so now that we have seen some approaches to hyperparameter optimization, the question is when to use which algorithm. And I would like to present here an overview which was adapted from a colleague, but is also sprinkled with my own experiences from doing HPO on the large scale for quite some time now. So yeah, let's start. When you look at the problem, the hyperparameter search space for your model, if that search space is very small, very low dimensional, has maybe just two hyperparameters you want to optimize, then it's probably still the best idea to do random search or grid search. As a starting point, as I already mentioned, both are embarrassingly parallel, so you can run all of the trials independent from each other. There's little overhead and almost no communication between trials required, but of course you're wasting lots of resources. But if your search space is so small, then you probably don't care about that. However, if your search space is larger than, let's say, 3 parameters, the next thing you want to look at is how long does each of your trials train. Now, if the computing time which is required per trial is very low, maybe less than 5 minutes, then you can probably still afford to do a random search, especially with HPC or cloud resources. You just let it run for a few hours and you have a good selection of hyperparameters. But usually, especially with deep neural networks, we know that training such a thing can take hours or days even. So in this case, you really start looking at these adaptive scheduling methods that I presented you earlier. However, again, one thing to keep in mind is if your model or your problem could be considered a late learner. And late learner means what I've also hinted earlier again, that the largest improvement of training happens in the second half, or the largest improvement to your loss happens in the second half of training, because when you're doing successive halving in this case, then of course you might be terminating some trials that get better later on. But typically, this is not the case, I would say. So most learning curves in classical neural network training that I have seen look like this, where you have like a very steep increase in the first few epochs, and then a very gradual increase for the remaining largest amount of epochs. So in those cases, it's very rare that you have a trial that starts out very bad and then at the end really catches up to become the top performing trials. you see that the trials that start out low here also end up on the lower part here after 200 epochs. So usually I would say you don't have late learners, and in those things it's safe to stick to these scheduling methods such as Hyperband or Asha. If, however, you're sure that your method or that your models are these so-called late learners, then it might be worth it to look at Bayesian optimization, especially if you cannot afford so many trials. So if you're limited by compute resources and your number of trials is, let's say, lower than 200, then it could be worth it to take advantage of Bayesian optimization, which can be more sample efficient, or maybe combine it with Hyperband to get at least a bit more of resource efficiency. However, if you have can afford to run a very, very large number of trials, then you basically get back to random search or Asha, which is very helpful with these large amount of trials and asynchronous successive halving. So with large cloud or HPC systems, especially Asha is probably one of the best things you can do. Another special case, again, are these non-stationary or dynamic values, in which case you should use the PBD, this population-based training scheduler. There are also some completely different approaches to the problem. For example, you can use reinforcement learning. In this case, a reinforcement learning agent would select the hyperparameter combinations and then get the performance of the trial as a reward, and learn from that how to pick better hyperparameter combinations. If you use a special representation of your architecture search space, it actually becomes possible to compute gradients and actually do gradient descent on your hyperparameter search space, which is something called differentiable architecture search. But this is your search space needs to have a specific representation in order to be able to do this. Other very interesting work look at so-called zero-cost proxies and how they relate to the final performance of a model. So one of these computationally cheap metric that you can look at, for example, is just the number of parameters of your model, and make a prediction of how well it will train based on that. It's been shown in literature that this works surprisingly well sometimes. And now we're in the time of very large foundation models, of course, where you can, because they cost millions of GPU hours to train, can only afford really one training run. So what you need to do here is to train a few models which are much smaller in size, and then look at how to transfer the parameters from these small models to the larger models, which is something that's called transfer and works very well on language models. Another issue I want to touch upon here is the overfitting problem. So usually you evaluate the performance of a hyperparameter configuration on your validation set, which stays fixed. But when you do heavy hyperparameter optimization, you can, of course, also overfit on that. So one way to fight this overfitting problem is to do, for example, post hoc and ensembles. So in this case, you would not take your one top performing models, but maybe take the top 3 performing models and average out their prediction. Another thing to do is to look at cross-validation. So measure the performance instead of measuring the performance of your model on a final fixed data set, you do this cross-validation and train it on part of the data set and then remain it on validate it on the remaining split. It has been also shown in literature that this is very effective, but of course it's computationally very expensive as you need to train each of your hyperparameter configurations multiple times. And what I've seen in my research is that actually using lower than single precision calculations can help to improve the generalization performance of your hyperparameter optimization, because when you're doing lower precision computations such as mixed precision, you get a regularization effect, and this can also lead can fight against this overfitting problem. Okay, so as last thing for this first section of the lecture, I want to give you a few more practical insights. So the first is, when you do hyperparameter optimization, don't just do a neural architecture search or classical HPO, but do both at the same time. So don't just optimize your optimizer related and architectural parameters one after the other, but yeah, try to keep them in the same search space, because one can heavily influence the other one. Especially with this hyperband or ASHA methods, it is really worth it to play a bit with the aggression factor. So what I mentioned in the last slides always was that you can keep the top 50% of trials, but experience has really shown that you can be even more aggressive. So keeping only the top 30% or just the top 25% of the best performing trials is usually sufficient. And that means that you're, of course, terminating even more trials, which saves you a lot of computational resources. One other thing that is especially important, when you're working on GPUs or have lots of GPUs available to run your problem, I would not try to treat the batch size as a hyperparameter. So generally, of course, smaller batch sizes can give you better generalization performance, but it also takes much longer for the model to train them. So what I would recommend here is to increase the batch size to as much as your GPU memory can handle, and then instead focus on optimizing the learning rate. Yeah, when you design your search spaces, you need to select the intervals that you sample your parameters from with great care. One thing that is one hyperparameter that is very sensitive to sampling interval is the weight decay value. So if you pick that too large, your model will basically learn nothing, even though all your other hyperparameters, such as learning rate or momentum, might be at the perfect spot. Just because weight decay is so extremely sensitive, it can crush your whole training runs. So those parameters you should always select with great care. And the last point, is very important. I already mentioned this in the beginning, but I would like to repeat it here again, because you still also in the literature see sometimes people who don't do this the right way. When you do HPO, you need to have 3 data sets. You need a training set for training the models, a validation set for which you will use for picking the best hyperparameters, and then you need a separate, completely untouched so-called test data set where you then evaluate the final performance of the model. Okay, I think with this, I think we can conclude the first part of the lecture.
Excellent work, Marcel. Excellent lecture. Thank you very much. And I think the students get the message that is here at the last bullet, because essentially what we ended up in 11.1, if you remember, we had one of the diagrams I was introduced earlier, with the validation idea again, validation sets, training sets, put everything back in the pot, but keep the test set in some corner, forget about it, just put it out at the very end, and then test your performance really. So validation sets are only used for model selection. Then you train everything around it. Also several terms I think you have heard already, cross-validation, that is exactly what you're right now doing in assignment 3, I hope, all of you, right? With the recommender engine, for instance, we said, so we have a 5-fold there. You could do the extreme with a 1-fold, that would be extremely computationally expensive. But yeah, I think the first part was already great, and we maybe just cut here for 10 minutes and then get started afterwards with the second part of the lecture. So thank you very much again, Marcel.